Good morning, everybody. So this is
Good
the
morning, sir.
last before the midsem exam. I believe your exam is on 3rd, right?
Yes, sir.
Okay, so please check it. I think most likely it's on 3rd, and accordingly, the during the scheduled time we will have the exam. Okay, so I will also post the details on classroom, Google Classroom. Okay, but we will go as per the schedule only. Okay, so there will be 2-hour exam, and during that we will have that model based test as quiz one or homework. The same pattern you will get for this midterm exam as well. Okay. Okay, so today we will continue with solving some tutorial problems, and yesterday I forgot to actually click record, so the recording not there, but we have the notes, and basically it was tutorial, so we solved some problems. Okay, so we will continue this problem solving because this is the one where you get the variety basically. So far in the lectures, we have assumed typically we took one very simple example and we solved it. But the idea was to, if you can solve the simple one, if you know the procedure, you can apply the same thing to even difficult ones. So in the problems, exercise problems, you see they have a variety of problems and they're all difficulty levels. So it's good to solve them. So I'm solving with you. Although I don't go into details. The idea is if you can find out how you can find how you compose the stiffness matrix and force vector. That's what you have to do. Rest is you can solve yourself. Okay, so we will now continue. So today we will have a start with 5.8. Okay, it says that develop a finite element equations for heat conduction with surface convection. Yeah, the strong form in this case is given by. So finite element equations it is talking about, right? So already we have in fact derived this equation Ka, okay, d square t over dx square equal to beta h t minus t infinity for x, okay, and given all those k, a, h, beta, t infinity constants, and beta is given by 2 pi r perimeter of the fin. Yeah, so this equation we actually have already, we actually derived it in one of the lectures, and we also had the source included here. So we had this plus sx, but sx equal to 0 in this case. There is no body source, so finally it will come like this one. Okay, so how do you do it? Uh, Basically very easy. You have to write everything at one side, so it becomes ka d square t dx square, right? Then becomes minus bh, right? Or you can write plus, doesn't matter anyway. Let it have minus only. Okay, beta h t minus t infinity is equal to 0, and you want to have a weak formulation, so 0 to L, small l, and then you have W, and then you have Ka ds square t dx square minus beta h t minus t infinity. Yeah. Okay, so and then you have dx is equal to 0. Okay, then integration by parts the way you have done. So W, then multiplied by, you have Ka is constant, so you will have simply W times Ka dt over dx. Yeah, you will have here L to 0 minus 0 to L, and you have dw over dx Ka and dt over dx. Done. And then you have minus 0 to L, and then W beta H t minus t infinity, right? Dx equal to 0. So here, depending on the boundary condition you have to give here. So boundary condition is not given as such in this case, but this is how this will remain like this one. Here you have derivative of W and T both here. You can separate them out. So W and T will multiply, and then you have WH and T infinity. Yeah, so accordingly, you can you have only W in one case, for example, right? When this multiplies to T infinity, here W multiplies to T. Yeah. Okay, so this is how it is. You can now get W T as a function of, now it depends on what kind of like element you want to choose. Accordingly you can write, right? So this becomes I equal to 1 to n, and then W Wi, not this is T, so you have Nix times Ti. Similarly, W is equal to, okay, so 1 to n Nix Wi, right? So regardless, general purpose we are making, regardless of how many nodes you have in the element, and you put those values here. Yeah. Okay, and accordingly you get here the values. If W, you get the W at L, which will be the last one, right? W at 0, you will be the first one, W1. Yeah, so this will be Wn multiplied by, so basically you can write or WL, which will be Wn, then Ka, then dt over dx at x equal to L minus W1, because W0, right? W at x equal to 0, so W1 Ka dt over dx at x equal to 0, then minus, right? Minus, and you will have what? Here you will have W1 to Wn, right? Then you will have K, and then K1, you write it K1 here, K1 K, which is coming from the derivative one, right? So we write K1 like this one, yeah? And then you have W T1, T2 to Tn. So this is because of this, because of second this, yeah? And then we also have the third one. Third one is because of just this, because T, W times T is there. Yeah, then we have plus, we have something, minus plus becomes plus as well. So we write, okay, minus, we will have a W1, W2 to Wn, write K2, yeah, and here also it will be T1, T2 to Tn, yeah. Okay, so because we have minus here, and then we have minus plus, so there will be another one. Here it will be, right, plus, we have W1, W2 to Wn, and multiplied by some f vector, let's call f. Now, only thing is what is K1, what is K2, what is K3. So K1 will be coming from, so let's call it K1, 11, K1, 12, and so on, right? Where K1 Ij will be equal to 0 to L, Ka, and you will have dni dx, dnj dx. Okay. Now, similarly, you can say K2 is equal to K211, K212, and so on. Yeah. So both will be n by n matrix. This is n by n matrix. Yeah. And K2 Ij will be equal to 0 to L. And see here, if you see, this one has W times T, right? W times T. So W is NIW1 plus like that, and T will be equal to N1 times T1 plus like that. So we have beta H, which will be there. So we will have beta times H Ni Nj dx. Okay, so there will be two types of stiffness, one coming from the derivative type, the other coming from without derivative. It is there in the expression, right? So this is coming because of the convection, this term is coming from the conduction. Or in stress analysis, there is no this kind of thing here, only this, so you get there. But in convection, you get this. So there are two types of stiffness. They will be added together basically. So this is how you get. Okay, so we get the, so you got K1, you got K2. Now only thing is we have to find out what the F is. Yeah, so F is where F will be given by, so you can see which all things are there. Things are beta H is there, and then T infinity is there, and that multiplies by W, which is N1 W1 plus N2 W2. So that means basically what you get is N, right? It has N terms, so N multiplied by T infinity beta H. So what you get here is 0 to L beta H T infinity N I, right? So this F, you can say Fi equal to dx. So F is composed of F1 to Fn transpose, where Fi is given by 0 to L beta H T infinity Ni dx. Yeah, so that's it. Rest you know how to put it in the matrix form and you can solve it. Any question, guys? Any question? Okay. If there is no question, we will move to 5.9. Okay, and 5.9 is more about the MATLAB code. Okay, so for a heat conduction MATLAB code, so I will see. I will send you a couple of program files. Okay, so anyway, this is about the MATLAB code, so you can do it. You can apply. So this is talking about for 5.8, how to solve 5.8. 5.9 is nothing but MATLAB code applied to 5.8. Yeah, so I will have for some problem, not necessarily for this one, but you can also program yourself. Okay, now let's look at 5.12, 5.10 and 5.11. I will leave it on you. Also, it's not important for us. So whatever we study, let's focus on that only. Okay. So as such, this course is vast. Basically, there are a lot of things there, but we will just learn those which are the most important ones. Okay. So 5.1 and 5.1, 5.11 or 5.11, that introduces you to different kind of methods. Yeah. And you can just work yourself, and you will be introduced to that method. Okay. Otherwise, for this course, it is not that important, and it's not popular actually, and hence we don't we haven't studied. Even if you don't solve 5.10 and 5.11, it's fine, but you can try. Okay, now 5.12. Okay, it says like given an elastic bar of length L is given equal to 4 meter, and the cross-sectional area A is given to be 0.1 meter square, and piecewise constant Young modulus as shown in figure. So we have something like this one, and we have x equal to 0, x equal to L over 2, x equal to L, and then you have E1, some value given 10 to power 5 Newton Pascal, and then E2 is 10 to power 8 Pascal. Yeah. So these two has like a different E now. Okay. Okay. Now the bar is constrained at x equal to 4. Okay. So constrained, the bar is constrained at x equal to 4. So here it is constrained, so you can like this. Yeah. And as a prescribed traction T bar is equal to 500 Newton per meter square acts at x equal to 0 in the positive x direction. Okay. So it said traction is there, and also at the same time it says that in the positive x direction. Yes. So traction positive x direction. So that means it already tells you which direction it will be. So fine. And consider a finite element mesh consisting of a single two noded element. Okay. So just two nodes here and here. Yeah. So number 1 and 2. Yeah. And then you have to do everything, stiffness matrix, force matrix, strains, you have to find out displacements, you have to find out, model the problem with two spring elements, solve for unknown displacements using the technique learned. Okay, it's also telling you that you make two spring, one here and one here, and then you solve it. Okay, and then you have to compare the results, you have to find out which one is better. Then if you model the bar with two linear elements, now one element here and another element here, so two noded elements, then you have to find out, or with one quadratic element, so three noded elements, and then you have to find out what will be the solution. So what is an optimal finite element mesh for this problem? An optimal mesh is defined as the one that gives the best one-dimensional solution. Okay, with minimum finite element nodes. Okay, so this is the question. Number 8 is in terms of design of finite element meshes, what kind of a recommendation can you make based on the results of this problem? Yeah. So in terms of design of finite element meshes, what kind of a recommendation can you make based on the results of this problem? Okay. So anyway, looking at it, if you see, the problem is very simple. Yeah. And if you have only one element, then how to approach it? So let us say first we have to condition. So this is fixed here. So what we know here in like 1, 2 noded element. Yeah, 1, 2 noded element, and what will we do? We are going to have first of all the boundary condition. So we have u1 and u2. So let's write u1, u2. Yeah, and then we have u2 equal to 0, right? And you will have u1 and 0, right? Right. Force, we don't have anything, but it says there's a T bar. This is a T bar, and this is the stress. Traction, it is telling you that really means it's the stress. Yeah. So F will be F1, which will be in, it says positive x direction. It says that. So you don't have to even figure out what is the meaning of T bar. We say F1 equal to 500 Newton per meter square multiplied by area, right? Into area 0.1 meter square. So that means 50 Newton. Yeah, in x direction. So F1 will be 50. F2 we don't know. That will be just a reaction. So we can, F2 is equal to R2, reaction only. So we'll put R2. So basically F will be equal to our 50 and then R2 transpose of that. What is the K? Again, K you have to find out. And when you have only one, then Kij is equal to 0 to L EA, and then dN over dN I dx dnj dx. Okay, where Ni x equal to 1 minus x over L. So that means dN 1, this is 1, dx equal to minus 1 over, so let it be capital L, and similarly n to x equal to x over L, dn2 over dx equal to 1 over L, right? So what we get here is K 1 will be equal to, for example, 0 to L, and then we have E, then area is given A, and then we have minus 1 over L square dx is equal to, now we have different E, right? We have different in E. Here E is different, here E is different. So what we will do, we are going to 0 to L, E1 A 1 over L square dx plus L over 2. Then L over 2 to L, and then we will have E2 A L square dx. Yeah, so finally what we get? We get E1 A. So E1A over L square, and then you get what you get here, x, and then you get L over 2 0 plus E2A L square x, and you get L over 2, right? So that's what we will get from here. Okay, and equal to E1 A L square L over 2 plus E2A L square and L over 2, right? So this will be simply the E1 plus E2 divided by 2, this average of the two stiffnesses, right? So E1 plus E2 divided by 2, so average of the two, A over L. So is equal to E equivalent, right? Let's sort E naught A over L, where E naught is equal to average of the So this tells you average, right? Okay. Now, and then you do the other things, like you know that, I mean, if this is like that, then K will be simply E naught A over L 1 minus 1 minus 1 1. Yeah, and then you solve it. E naught A over L 1 minus 1 minus 1 1, and then you have U1, we don't know, U2 is equal to 0, is equal to, we have the 50 here, and we don't know, this is R2 here, and you solve for it, and what you will get? You will get E naught A over L U1 is equal to 50. Yeah, and then you know this, you know this, you know this, everything you can find out U1, and rest our other things can be found out. Okay, now looking at this, what is the problem? Problem is if you have a spring, right? You know that when you have a spring, two springs K1 and K2, then if it is in series, then the K is given by what? It will be K1 times K1 times K2 divided by K1 plus K2, right? You agree?
Yes, sir.
Yeah. So that means the average that he has calculated is wrong in this case, right? So it is just taken average of the two, but the actual, it will be like that. Yeah. Solution is different. So that's why it asks you to compare. Okay. Now, when you take two of them, then what happens? Yeah. So then, if you take two of them, so here, right, you have 1, 2, and 3. And then you will have, now let's call it L, a small l, which will be equal to big L over 2 now, right? So this is L over 2, this is L over 2, and this is equal to a small l. Let's call it like this. Okay, so now in that case, what happens? We have E1 here, E2 here. So accordingly, you can find out K is equal to, you will have EA over L, and then you have E1 minus E1 minus E1, E1 plus E2, E2 minus E2 minus E2, E2, right? 0, 0. Yeah, and then we have we can U vectors becomes what? We don't know the first one, U1, we don't know the second one, U2, and we have the 0. Transpose of that, force, we have the 50, first one, second one is 0, third one we don't know, so we have the R3 like this, and then your equation becomes A over L, then you have E1 minus E1 0 minus E1, E1 plus E2 minus E2 minus E2, E2 0, then you have 0 U, sorry, then we have here we don't know, so U1, U2, and then U0 is equal to, right? Then we have 50 here, then 0, no force there, and then you have R3, and then you solve it. Yeah. So when you solve it, we are going to solve, this is 0 here, so this and this go away, so you have just this, so A over L, and then you have E1 minus E1 minus E1, E1 plus E2, right? And then you have U1, U2 is equal to 50, 0. Yeah, and then you invert it now. Yeah, then this becomes U1, U2 is equal to L over A, and then 1 over, so you will have E1 square, E1, E2 minus E1 square. So E1, E2 only. So E1, E2, right? Okay, and then you have E1 plus E2, E1, 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 and then you have 50, 0. Yeah. So what you will see now that you will get the exact solution in that case, what it's supposed to have. Yeah. Automatically you will have E1, E2 automatically there. You can find out that. Yeah. Got it, guys? You will get in this case the exact solution because you know that earlier also that when you have two of them, two springs in series, then you got the exact solution in the second chapter. Yeah. So if you work out, you will get the exact solution. You can assume it to be two springs. You can find out what the solution is. Whatever you get here, you will match there because you have taken two elements like that. Yeah. Third part, when it says that if you have only one element and then you use a quadratic element, yeah. So what happens? If you try to calculate the u, then what is the problem? Just a minute, guys. I have an urgent call, so just a minute. Yeah, sorry, guys. Okay, so we have to look at based on the solution. Like if you consider it as two springs, then what happens? Our K will be E1 A over L, and K1, K2 will be equal to E2 A over L. Yeah, and hence, uh, because of that, our force is the same in the both the cases, right? You have the same force. So you are fixing it here. You're applying force F here. It will have same force. So you can find out that like in this case, just for the second spring, what will be the U? U will be equal to F over K2, right? And that will be equal to F L over E2A. This is just because of this spring. Similarly, for the first spring, you will have, let's write this one is contribution, right? So I will just say U2 like this, right? Okay, now U1, just contribution of because of that. So it will be F, same force, FL over E1A, right? So that means you can find out that how our the U will change. So U3 will be equal to 0. U1 as U2 will be equal to FL over E2A, because this is the one that will dictate what the displacement of this will be. And this, U1 will be both this plus this, because this is going to displace this also. This is going to displace whatever this I displaced plus, because this is spring, what displacement is, both of them together. So U1 will be equal to FL E1A plus FL E2A, right? So this is how it is going to be, right? Okay, so that means if you have our U1, we know that our U1 is like this, U2 is like this, U3 is like this. So we can actually plot how it looks like. And you know that it is going to vary linearly between this and this. In actual, so what I mean to say is the exact solution is like this. Exact solution is like this. So you get 0 to L here, and there is L over 2, and then you have at x equal to L value is 0, and then here we have some value, and then linearly varies from here to here and like that. So it will be something like, let us say like this. It will have like from to here and then here to here. So goes linearly from here to here. Yeah, or it could be some other way also. It could be like, it could be even like this. It goes from here to here, goes here to here. Yeah, if it is too stiff, then it will go like this. It depends on which one is both same stiffness, then it will be a straight line. If this is stiffer, the first one, then it will go like this. If the second one is stiffer, then it will go like this. Yeah. So this is how it will do, meaning that the exact solution has a kink. And in that case, what kind of meshing will help? You know that since this is piecewise line, so hence this will help when the most optimal is when you use two elements with one at this node. That's it. If you use one, then it is going to find out the average. It will just find out this somewhere. If you use the two of them, then it is going to find out the exact. And if you are going to use the let us say the three-noded element, then it is going to be a smooth, right? Three-noded element will go something like this. Something like this it will go. This is three-noded. So there will be some error, because why? Because the trial function itself is quadratic. You are assuming it to be quadratic to begin with, and hence the answer will be quadratic only, and hence there will be error. Yeah. Any question, guys? So this gives you good understanding. Yeah.
Sir,
Yes.
then this means that if we take the trial function to be as close to the original function that we have, then we will be having good results, exact results.
Yeah.
Okay. And if we we cannot just increase the degree of our polynomial trial function polynomial like that only, like without any understanding of like going with more constant is not good in every case.
Yes.
Okay.
True.
Okay.
That is true.
Okay, sir.
Yes. Hence, you should know, you should have some idea about what kind of solution it will be. And typically, if you have the discontinuity, if you have something as smooth, some area is uniform, for example, or material property is uniform, so then you know that everything will be continuous. You will be continuous and all. Here also is a continuous, but only the matter of your strain becomes different. Because of E, strain will be different, because material property affects the strain. That means the slope will change. That only tells you the slope will change. But when you are giving a higher order polynomial slope, it will maintain the slope. So only when you have the piecewise polynomial, it has capability to incorporate the slope as well. Yes, accordingly you have to give. Yeah. Okay. Any other questions? Okay, guys. So now let's move to 5.13. And it says consider a three-noded quadratic element in one dimension with unequally spaced nodes. So now it is telling that your nodes are not at middle, but this is something like this. So node number 1, 2, and 3, and this is fixed here. Yeah, and you have x here. Yeah, then it telling what is it telling? Telling that you have to obtain BE matrix. B matrix, as you know, that this will be B is nothing but del dn1 dx, dn2 dx, and so on. Yeah. Okay. Then consider an element with x1 equal to 0, x2 equal to some value is given. Evaluate a strain in terms of u1, u2, and check what happens when z approaches 0, the xi approaches 0, and so on. If you evaluate Ke by 1-point quadrature using for some coordinates as in B. So it is asking you to evaluate do the integration using the Gauss quadrature, and that too 1-point quadrature only. Okay. Then if ux in part B is given by half x square at nodes, then it is asking you some question. So basically here the idea is to explore when you have the length which is the nodes which are not equally distance from each other, right? So middle node, this one is not equal to this one. Then what happens? Yeah. Okay. So how do you do it? So here you have x1 equal to some value. So x equal to 0 you can have, and here x equal to L, let us say, and here it will have, or you can say this is x1, this is x3, this is x2, like that. This one is basically you can compose basically the various ways. It is what you can do is n1, for example, you can have x in x, and depending where it is, so let's say this is at x2, this is at L, this is equal to 0. Yeah, or x2 equal to, let's say, call it A, so that it becomes easier to derive. So n1x becomes, as you know, that this will have zeros at A and L. So accordingly we'll write, so C1 x minus A, right? Then x minus L. And you know that at x equal to 0, this is equal to 1. So n1 0 is 1 equal to C1 minus A minus L. And hence C1 equal to 1 over AL. And hence n1 x equal to 1 over AL, x minus A, x minus L. Yeah. And so on. Similarly, N2 you can write N2 x is equal to C2 x minus L, and you know that N2 A is equal to 1. That means C2 A minus L is equal to 1, and C2 equal to 1 over A minus L. Hence N2x is equal to 1 over A minus L x minus L. Right? Similarly, N3x is equal to C3. Then you have x, right? X minus A. And accordingly, N3L is equal to 1 is equal to C3L L minus A. That makes C3 is equal to 1 over L minus A. And in 3, X is given by 1 over L minus A. Then you have X minus A. So you got all the three. And you just have to find out BE is nothing but equal to dn1 dx, dn2 dx, dn3 dx. Right? So just you find out. That's it. That's what you have to find out. Okay, now what it is asking next one is consider an element with x1 equal to 0. So x1 equal to 0, that we have assumed it. X2 equal to 1 over 4, that means A equal to 1 over 4 and L is equal to 1. Okay, now it says evaluate a strain in terms of U2 and U3. Yeah, and check what happens when xi approaches 0. Okay, here xi, where the xi coming from? There's something wrong. Yeah, so 5.23, figure 5.23. Okay, guys, there's something wrong in this question, part B, because suddenly it gives a reference to xi. Okay, so xi approaches 0. No idea what it's talking about. Yeah. But in any case, we can construct it, and what we have is epsilon is equal to BE and then U, right? UE. And so what you can do is, given these values, you can find out what is the value of this one, evaluate this one multiplied by UE. U is given like U is equal to 0, U2 and U3, like this one, and then it will have like this. Oh, I got it. What it may be saying that the second point may be approaching to 0. Then what happens? You got it? So it's not xi. I think you should call it this. If A approaches zeros, then what happens? Then these two will coincide, right? This will go to this one then. Here. Yeah. Then it is asking you what will happen to the strain. So you do the numerical experiment, you do that. So what it is telling you, when A approaches 0, then what happens? Yeah, although it says xi here, but I think typing mistake. It should be when x2 approaches 0. That's what that is, and so on. Okay, so this is a matter of evaluating this value and then seeing how it is. But main thing here is how to calculate, how to find out the shape functions that we have done. The rest you can do yourself. Any question, guys? Any question? Okay, let's take up one more question, and after that you can do yourself. All others. Basically, there is no much varieties. All are like easy questions only, and then you can do. But one, I think 5.14 is something give you some perspective that will be useful. And so quickly in 5 minutes we'll try to solve it. I mean, the method we'll discuss. What it tells you is a tapered rod, which is something like this, and it has it goes like this, and it says that A xi is given as A1 1 minus xi plus A2 xi, and where it says xi is equal to x over L. So this is x, this one is L here, L, and x coordinate system, we have the xi coordinate system. We are composing this one like this one. Yeah, you can do it. A as a, we have A1 here and we have A2 here, right? So if linearly A is linearly increasing, then you can write also in like this one, right? So A1, meaning that you can actually write A is equal to N1 A1 plus N2 A2. It is simply like this, right? If you can write as X, uh, like if you can write U as a combination of N1 and N2, you can also write area as a combination of N1 and N2 if it is linearly increasing, right? So that's how it is written. Anyway, this is this just to mention here that we can also write this way. Now, second thing is our U obtain the element stiffness for a linear displacement element with Young's modulus equal to E by using K equal to, so all other things you have to find out. Find the stiffness matrix using displacement vector. Yeah. So number 8, it's a linear displacement element, means two noded element. First one is talking about with Young's modulus E, and then second, B is asking you when U is given by U1 plus U2 minus U1 xi square. So this is giving you the interpolation function to begin with, right? And then you have to compose this one accordingly. Yeah. So how to do it? Now the first one, when you have two noded element, then you know that you have Kij is equal to 0 to L. Yeah. And then what do you do? When you have E, A, dn I dx, dnj over dx, dx. Right? So you do like this. Then what is the next one? Here we know that n1x is equal to 1 minus x over L, which is equal to 1 minus xi. N2x is equal to x over L equal to xi. Right? So we are converting into the, since xi equal to x over L, d xi equal to 1 over L dx. So that means Kij we can convert from 0 to 1, then E, A, then we have so this becomes N1 in terms of xi, this is N2 in terms of xi, right? EA, and then we have D N. Okay, so we also have to write how dx over. Okay, first let us convert that. Sorry. Okay, so if n1 dn1 over dx is equal to what? Will be equal to 1 over minus 1 over L, minus 1 over L, right? This we could have written also like this: dn1 over dxi, dn1 over dx equal to, or dni over dx equal to dni over d xi and d xi over dx. Yeah, we can also write like this one. So, and what is this? We can exactly write like this one only, And this is nothing but d xi over dx is what? So we can write it here. So x xi is equal to x over L d xi over dx equal to 1 over L. So equal to 1 over L dni d xi. Yeah. So coming back to here, we have EA and then we have dni dx, right? So we can write 1 over L dni d xi dnj over d xi. In both the cases, then we have to write L square and d. Then we have 1 over L. So see here, we have dx here. So d xi dx equal to L times d xi. So we have to write here L times d xi. So just to tell you that there is a, when you convert, when you change the coordinate system, accordingly, lot of things changes accordingly, right? So you have E, then A, dni d xi, dnj d xi, and then you have 1 over d xi, 1 over L d xi. 1 over L because you have L here, then divided by L square. Now that A is given as A as a function of xi is given as A1 1 minus xi plus A2 xi. It will fit here now. You can put this value here. And you can, so Kij equal to 0 to L, E is a constant, then you have A1 1 minus xi plus A2 xi, right? And then you can have the values of this, whatever you get, dni d xi dnj d xi over L. Okay. More of this we will learn later on. Okay, when you are working in different kind of elements, then sometimes we have to change this coordinate system to make it life easy. Okay, so that we will do when you are studying 2D problems. Okay, but that is all for today. Any question? Okay, there is no question. Okay, all the best with your midsem exam. Okay, tomorrow I will post the homework also, so, but I will give you some time. Okay, and that is all. All the best.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.